Thank you, Marco. I apologize for not being an archaeologist or a geologist, not an expert really in fish ponds or tanks, and to give you a presentation which is only partly addressing the issue of fish tanks. I am hydraulic civil engineer, professor in coastal and harbor engineer, and therefore my presentation will also give you a very quick and general overview of the development, of the progress of my discipline in history, in ancient history, which I provide also to my student of my course, because I think it's useful to have this background. Being a Roman, really proud of our ancestors, and I also made classical study. I used to come exactly in this place since my childhood for summer holidays. Okay, let's go on. This is just a short overview of some of the main references. In particular, I will refer to the significant work carried out by the Americans in the Romacons project a few years ago. Building for Eternity gives you a lot of details about the material composition of the structures in our fish ponds and, of course, in the harbor works. I also made some articles and papers in the past regarding the history of coastal engineering. Okay. And this is a map of the Mediterranean where, of course, it all began, and we have still really many remains of coastal and harbor structures all around. Here mentioned some main locations. There is an inventory of more than 4,500 structures and ports by my colleague, engineer Arthur de Grau from France, that you can see here. So, relating to Nick Fleming's question, I think you can maybe also use other harbor structure as indicators of sea level rise. In this map, I also shown the main feature of the Alexandria Lighthouse, which was the highest building for millennium. It just collapsed to an earthquake in the 13th and 14th centuries, and the beautiful annular-shaped military harbor of Carthage. Okay, so this is an example dating back to what Jean-Philippe showed before in the beautiful site of Tyre in Lebanon. Just an example. After, of course, the earliest sea works in the Egyptian time, of the Phoenician engineers, which were really the first maritime engineers in antiquity. And as all the harbors in the antiquity, they were, of course, built near islands, peninsulas, in sheltered areas. But what I want to stress is that, as you can see, there was an hydraulic connection. There were multiple harbors, north and south, with multiple entrances. And this is just because the main problem in the Mediterranean Sea is the lack of tides, the lack of currents, and the risk of siltation. So, since then, the hydraulic engineers had to enhance the currents to fight the siltation issue. Of course, also there was a reason to have different ports for different wind condition, also different traffic, military, fishing, and commercial. Let's go on. So this is some picture from Tyre, which I took years ago. They also developed the technique of blockwork structures for quay walls, and as you can see, they rely upon friction. The blocks made of rock were connected without any mortar. And hydraulically, they developed a very ingenious idea of collecting, overtopping water over the rocky ramp in a tank, and then release into the harbor to flush, to exchange the water and avoid the siltation. Of course, most of the quay walls were indeed created by cutting the natural rock. And the Romans copied this idea, and we can still see it in the beautiful port of Ventotene, Vandataria, not far from here, where the the rocky coast was curved and a channel was digged to collect the overtopping water. You can still see here near the entrance. You can still see the bollards where they used to put the chains to close the harbor at night. And interesting is to see that this idea of collecting the overtopping water at a higher level and then release is now used by my colleagues to produce energy. So we have a station now in Naples Harbor, and which is working by activating a turbine. So it's a totally different scope. Of course, also to avoid stagnation of water in marinas. So we need the system to increase the flushing, because now we can dredge, so we don't need really, siltation is not such a big problem. Go on. And also, well, after the Phoenicians, the Greeks came. They also used multiple harbors, like in Rhodos, closed with chains. But interesting is the Greeks used to put windmills on the breakwater to produce energy. And if you go to Rhodos, you can still see 3 of them on the breakwater. And today we build these turbines again in the sea and in the breakwater, because the wind is a bit stronger and a bit more uniform and with less visual impact. Okay? Okay, just a map of the main location. We come to the, let's say, imperial era of Roman times, 1st century before and after Christ. So we have many locations where we have fishing ponds and harbor works around this area. We are now here in Pirgi. And just north of here, 1 hour north, we have Cosa, now Ancedonia. Just to remind that the Etruscan and then the Romans took advantage of some cracks in the rocks and made an artificial one for the same scope, to have a natural flow of water across the breakwater to avoid the siltation. Let's go on. I think it's really a beautiful place to visit, because part of the channel is tunneled and it's still working. You can still see the grooves for the sluice gates. So this shows us that even before, in the 2nd, 3rd century before Christ, and even before, the Phoenician had the hydraulic capabilities to control the flow, as we need for fish ponds. But they could not build underwater. They only use rock or blocks, and only the Romans in the 1st century, we saw Portus Iulius and also in Cosa, Ancedonia. The great revolutionary discovery of the Romans engineers was the pozzolanic concrete, the hydraulic mortar that is created by mixing pozzolana, which is a pumiceous volcanic ash, which comes from the Pozzoliere, and the lime, the calx, which is obtained by cooking the limestone and turning it off with water, and mixing the pozzolana and lime in a volumetric ratio of 2:1, we get the hydraulic mortar, which hardens underwater. And of course, it is combined with aggregates, usually 60%, 40%, to get the marine concrete. What is interesting is that this material has a relatively low unit weight compared to modern concrete, which is about 2,300. And also the compressive strength is quite less. But nevertheless, the fracture energy can absorb is very high, and the durability is exceptional. Already the old authors mentioned these fantastic properties of this material. Okay, and of course this enabled the Romans to build any kind of structure, total flexibility, because concrete is casted with any shape. So they were free to build any structure at sea, and also in different conditions. Vitruvius made the first handbook of coastal harbor engineering, and he mentioned that in shallow water they just put some forms, wooden forms, to cast inside. When they had no marine concrete available, they used a double wall coffer dam to cast the concrete, and they emptied with pumps that make it dry. And when the water was a bit more rough, more exposed, they made precast concrete and then they lowered it down with ramps. Just more pictures from this nice French book about the construction procedure, the details of the beams and the poles, and also of all the workers, because they need to carry. It was really a fantastic logistic process to prepare all this material with basket and dump into the water. And okay, at the moment we are here, and just to show you that just off these windows we have also fishing ponds, Santa Severa, and this is the way it was constructed with the first method mentioned by Vitruvius. Usually there are two methods, casting side by side or making it in blocks. But this summary is just to remember that fish ponds are built in relatively sheltered waters, in rocky seabeds, so quite stables, and sometimes the rock cutting on site was also providing the aggregates for this marine concrete. And of course also Santa Liberata was just mentioned. You mentioned you have an aerial view of these fishing ponds. I mention this because this is the only fishing ponds which was cored, drilled during this Romacons project. All the rest were moles and breakwaters. So it was in 2004. And let's go on. They derived, cores from these walls with all the characteristics of the material which are listed. I have this book with me if you are interested, but easily available. Let's go on. Marco. This is also a picture of the characteristics, the crystalline and aluminium, calcium, silicate, hydrate, cache, and the mineralogic composition of these clasts, which is given for this course. So we have really a detailed picture of all the material composition. But what is interesting is that all the cores were made in many places all around the Mediterranean Sea, and the composition was really quite consistent, quite uniform. So the Roman engineers followed very strict rules and standards, and also in the big project of Caesarea, where about 20,000 cubic meter of pozzolanic was used, they probably shipped from Pozzuoli, because the ships were coming from Alexandria to carry the wheat, and then of course they need ballast to go the other way around. Okay, and finally I want to mention that in the Romacons project the American researcher also made a full replica of one of the pile, the walls made with marine concrete, and they made also cores after months, after years, and so they could demonstrate really the hardening process, the construction technique by the Romans, and reproduce it very successfully. Just to remind you that we have examples also inland. In the Fiumicino airport we had a big breakwater of the port of Claudius, which was built by sinking a full ship and ballasting with concrete. Other examples from other areas, mostly along this our coast here. So all structure which survived for more than 2,000 years. Just to remember that modern coastal engineering uses still this pozzolanic concrete for, let's say, more creative shapes that we use for armor blocks to protect our breakwaters. This is a picture of the tetrapods in front of our new University of Marine Engineering in Ostia. And of course, artists can make more creative solution afterwards, but they need flatter surface, so more cubes than tetrapods. Okay. The Romans also developed a new say type of structure, which is the vertical wall, also in dry condition. Of course, if the seabed was poor, they need to make piles, to drive piles before. And also the so-called caisson breakwater. We have the famous Sapri remains. Go ahead. And the first really known example are the caissons that Julius Caesar used to attack Pompeo in Brindisi in 55 BC, and the big ones used by King Herod in Caesarea Maritima in Israel in 18 BC. We still have remains underwater. You can visit it with scuba diving underwater. But this idea to let's say, to sink a big box with concrete was also used recently to support the D-Day in Normandy. So all our history in some way was conditioned by this engineering solution, because they construct a breakwater in a few days by just towing the caissons from England. And this is just an example of one of the structure, which is the deepest one in the world at the moment in Japan. Okay, just a quick mention to another topic, which is port layout, the design of the plan shape, and again to remind Ventotene, which is really for me a masterpiece built by Augustus in 14 BC. Just to remember that this shape is still working and used by the boats as central opening, an absorbing beach, and then all the keys for mooring in the lateral position. And this, let's say, layout is very similar to the one that was used for the latest, most recent port design in Italy, which is Gioia Tower, of course, on a quite different, larger scale. And go on. Of course, one of the characteristic port layout in the Roman times was the converging arms with the insula, with an external breakwater. Of course, this is not used anymore, because at that time the ships used the oars or the sails. So now it would be too complex for the maneuvering, but let's go on. This is also the layout of the big port of Claudius, which, as you know, stands where the Fiumicino airport is now, because the coastline advanced by a few kilometers since those times. But just I want to mention that a few years ago, together with Professor Nori, we studied a lot the real plan shape of this port. We also made some numerical simulation of wave penetration, and we demonstrated that indeed this layout, this configuration was exactly the one which was drawn by Peruzzi in the 16th century, and not other possible ideas which were proposed by other archaeologists in more recent times. So I think this exact configuration was also confirmed recently by archaeologists. And of course you can still visit the Orea and the Trajan hexagonal basin, which is also a beautiful place to visit. Okay. So just to finish, after the siltation of the port of Ostia, which was really important for the empire, Trajan moved the port to Civitavecchia, Centuncelle, not far from here. The designer was Apollodoro. And again, this model of layout became the ideal port layout in all the Renaissance period. Even Leonardo made a drawing of it, and Bernini was inspired by it when he designed the St. Peter's Square. So waiting for the pilgrims to come in the refuge of the church. But of course, this insula was destroyed when they built Via della Conciliazione more recently. Okay, today Civitavecchia, well, it was like this for many centuries. Only the last century, the insula was, let's say, connected to the shore, and so we have one long breakwater. Okay, just to finish, maybe to remember that Leonardo was also our proud coastal engineering. He made other design of this kind of harbors, and also more creative harbors like the spiral port, but especially was really the inventor of coastal engineering in terms of hydraulics, of the progressive nature of sea waves, breaking waves on walls, and so on. So we still have big heritage from his drawings and books. Conclusion, I think that despite the lack of scientific knowledge, very limited construction technology, the maritime engineering in antiquity was extremely developed, and the hydraulic and structural design, I think, can still inspire the present modern engineers. The main revolutionary innovation in the 1st century BC, so that is probably the date where also fish tanks started to be built, not only for socio-economical reason, the richness of the empire, but also for the new construction technology, which is well described by Vitruvius. So this material can have very strong properties to resist great longevity at sea. And this material has quite standard characteristics, and this compact, because the material is compact, but also the substratum is rocky, is quite hard. So I think that they really represent a good indicator for long-term changes of the sea levels. And finally, I want to mention that the experience and intuition of coastal and harbor engineers can be a valuable support to underwater archaeologists. I think sometimes a bit neglected.